Good evening. My name is Arun Kumar Awasthi. So let's start a machine learning project using environmental sensor data, which is predicting electric power output of a combined cycle power plant. So we use a data set of 9,568 hourly records, which has four features into it: template starting from 1.81 to 37.11, ambient pressure, which is 992.89 to 1033.3, relative humidity, which starts from 25.56 and goes up to 100.16, and the last exhaust vacuum, which is 25.36 to 81.56. Target is to net hourly electricity energy output P, which should be in between 420.26 to 495.76 megawatt. Our goal is to build a regression model to predict P using environmental conditions. So let's define the approach and the problem statement. This is a regression problem as the output is a continuous numerical value. I used all four features: temperature, ambience pressure, relative humidity, exhaust vacuum as inputs, since each contributes to the plant's efficiency and the output. Target is P, energy output. I consider three algorithms: linear regression, which is a sample baseline; random forest regression for capturing non-linear patterns; XGBoost regressor for high performance and structured data. I choose root mean square error RMSE as the evaluation matrix because it gives the higher weightage to larger errors, which is important in predicting energy output accurately. Model building process that I have started. What is the data required for the training, then test, split the data, and cross validation. So I split the data in data set into two sets, which is training set, which is 80% of the data, around 7,654 rows, and test data, which is 20% of the data, that is around 1,914 rows. This ensures the final model is tested on unseen data to evaluate its true performance. Cross validation. On the testing set, I applied five-fold cross validation. The data was divided into five parts. Each fold is used once for validation and the remaining for the training. This process helps in selecting the best model, turning hyperparameters, that is tree depth, learning rate, reducing the risk of overfitting. The goal is to build a model that generalizes well, not just memorizes the training data. Let's now talk about model performance. Linear regression, that you can see RMSE is 4.57, which is very fast, but missed non-linear interactions. Random forest regressor, RMSE is 3.64, performed significantly better, captured complex relationship as well. XGBoost regressor, wherein RMSE is 3.48, which is the best performance overall, but required more tuning. Final model chosen is XGBoost regressor due to the lower RMSE and consistent performance across the field. So model performance depicted in three paragraphs, three charts that you can see. Let's now visualize how our final model is performing. The first chart shows actual versus predictive values for XGBoost. The closer the points are the red diagonal line, the better the predictions, and you can see we are quite close. Next, the residual plot confirms that the prediction errors are fairly evenly distributed around zero with no significant outliers, which indicates a well fitted model. Lastly, the feature important chart highlights that temperature and exhaust vacuum are the most influential variables in the predicting the energy output. Together, these visuals give us the confidence in the model's accuracy and generalizability. The conclusion of this project is The summary of this project is developed a regression model to predict energy output of a combined cycle power plant. Used 4 environment features: temperature, ambient pressure, humidity, and exhaust vacuum. Approach that we took is tried multiple models: linear regression, random forest, and XGBoost. Used 5-fold cross-validation to ensure stable and reliable performance. Final output is XGBoost achieved the lowest RMSE 3.48, indicates the best accuracy. Model generalizes well to unseen data and captures complex patterns. Business value: this model can help optimize energy generation planning in real time, enables predictive operations with the potential cost and efficiency gains. Thank you.